So we were working with the beautiful property of inverse maps, and we wanted to prove that they work really well with intersection and union of sets. So let's see how we can do that. Let me remind you of the setup. This is a follow-up from the previous video. If you have not seen the previous video, you should go to the link in the description for that. This is X and this is Y, suppose. There are two spaces and we have a map F from X to Y. Mind it, this is not a continuous map or it doesn't have any special property. It's just a map from X to Y. And we want to show that if you take A and B as two sets inside Y, so they might be disjoint, they could have an intersection. F inverse A union B is equal to F inverse A union F inverse B. To make sure that we are on the same page, F inverse A union B is some sort of a set down here. Again, it doesn't need to be like this continuous chunk of X. It could be broken pieces, informally speaking. So F inverse A union B is a set down here, and what is the property of this set? That if you pick, so all X, or rather I should write all X inside this capital X. So this is a standard way of using notation. Small x denotes an element, capital X denotes the set. So for all x in X such that f of x is inside A, so this point either go inside A or it goes inside B. So or. Of course, two of these things may happen simultaneously if A and B has some sort of a intersection. So maybe I can make the picture a little bit better for the intersection. Maybe this is A and this is B, and it could happen that this point in here, it lands in the intersection zone, and then it would be both in A and in B. So no matter what is the case, f of x is in A or f of x is in B, this is the definition of this set. This is the collection, this set that I have shaded here is the collection of all such x in capital X such that this happens. Okay. So this is how the inverse map is sort of defined. Now we want to show that F inverse A union B is equal to F inverse A union F inverse B. Now whenever we are dealing with equivalence of two sets, and that's what you have to realize down here, we have two sets on both sides of this equation. Whenever we are dealing with equivalence of two sets, one way to go about it is the following. You show that the left hand side, that is in this case this particular set, is a subset of the right hand side, and the right hand side is a subset of the left hand side. If you can show both of these, that would simply imply that left hand side and right hand side, both of these sets are equal. This is a standard strategy of showing that two sets are equal. So let's do that. Suppose we pick an element from the left hand side. Suppose X belongs to F inverse A union B. By definition, this implies that f of x is inside A or f of x is inside B, because that's the definition of F inverse A union B. You get to be a member of this space, you get to be a member of this space, of this subset, only if you land up in A or you land up in B when F is applied on you. Alright. So f of x is in A or f of x is in B, but that would mean that either x is in f inverse A, so x is in f inverse A, or x is in f inverse B, right? Of course, if fx is in A, then x is in f inverse A. If fx is in B, then x is in f inverse B. But that, if we write in the notation of sets, that means x is in f inverse A union f inverse B. That's the meaning of x is in f inverse A or fx is in f inverse B. So if you carefully analyze what we did, we picked up an arbitrary element from f inverse A union B, which is here, and we showed that it's inside f inverse A union f inverse B. This would clearly imply that f inverse A union B is a subset of f inverse A union f inverse B. The same thing is true on the other way around. So let's quickly do the other way around, and I'll not spend much time on that. I'll pick one element from f inverse A union f inverse B. This implies f of x is in A or f of x is in B. And you should try this on your own before seeing the rest of the video. But that would mean f of x is in A union B. Of course, if it's in A or in B, then certainly it's in the union of both of these pieces. But that would mean x is in f inverse A union B. Whenever fx lands inside A union B, x is in f inverse A union B. So we conclusively proved that f inverse A union f inverse B is a subset of f inverse A union B. Why? Because we picked an arbitrary element from this set and showed that it is inside this one. Okay, so combining these two results, we now have exactly what we wanted. That is, f inverse A union B equals f inverse A union f inverse B. Now what you have to understand is what is more important than this particular proof is the essence of it. That is, firstly, inverse functions work really well with unions, and secondly, this strategy of proving equivalence of sets. So if you take nothing away from this particular video, take this, that inverse functions work really well with unions, and whenever you want to prove two sets are equivalent, show that each is the subset of another. Now let me quickly move to the other result that I would want you to show, and that is f inverse A intersection B is equal to f inverse A intersection f inverse B. Give it a try, and the proof follows exactly in the same way. Link in the description will take you to the first video of this sequence, and if we make another one on this particular result, it will also lead you to that. Keep watching and keep doing great mathematics, and if possible, subscribe to this channel. Thank you.